We're supposed to find a component form for the vector with the given magnitude and direction angle. So what they gave me is a length of a vector, and they told me where that vector was. I need to figure out where does that vector end? What is that point that vector ends? So a drawing of that might look like, if I want to do a rough sketch. I know I didn't give you a ton of room on the homework to do rough sketches, but it's always a good idea just to do a quick rough sketch of what they're actually providing us. Well, they're saying that's 145 degrees, so the angle from the x-axis there is going to go 145 degrees, which is about there-ish. Maybe a little further, but oh well. And what they're looking for is that point right there. I'm looking for that point right there. What is that A value and what's that B value? So our A value would be here. Our B value would be up here. So they're looking for vertical movement, horizontal movement. All right, that's our A and our B, and that's what we need for component form. Like I said, don't get in your head. Component form is, what is this point? What is that point? And then we use angle brackets. All right, so to find that point, first of all, I need to write down that it's 290, because this is our magnitude. Our magnitude is what is that length of the line. Magnitude's always positive. All right, if our magnitude is 290, and our angle is 145, that's everything I need to get my A and B values. Our A value is going to equal our magnitude times cosine of whatever our angle is. Once I know that, you should know B then. Because B is going to be magnitude times sine of whatever our angle is. And that's all we need. I have my magnitude, I have my angle, I just need to plug it in and see what answer I get out. So we're going to have A is going to equal our magnitude is 290 times the cosine of our angle, which it said it was 145 degrees. And we'll do the same thing for B. B equals 290 times sine of 145. What did I end up getting out? I got out A is going to equal negative 237.6. And I got B equaling 166.3. In component form, that would be negative 237.6, comma 166.3. Make sure you use those angle brackets, and this is our component form. And now, especially if I was on a test, I would just make sure those numbers actually make sense with the problem. So I said I'm looking for this point right here. Does it make sense that my A value is negative? Yeah. And should it be what, negative 237? Does that make sense with this being 290? I think that makes sense. And then our B is 166, so we go up positive 166. It matches our point. Now, if our vector would have had a magnitude of 10, those numbers wouldn't have made sense. Because if this was 10 and this was negative 237, you'd been like, I don't think I did that right. Yeah?
I have a question, like why, so like, you have the 145, so then the remainder of the 180 would be 35, right?
Yeah, so we're looking for the full angle is 145. There we go.
The rest of that would be 35. So why can't you do sine of 35 equals like x over 290?
X over 290. Oh, so you're saying instead of using 145, subtract 90 away from it?
So like that like...
Oh, this little bit here.
That equals 35.
Okay, that equals 35. You can, as long as you realize whether your value should be positive or negative.
Okay.
Okay?
Okay.
So there's a chance. So what Alex did is he used a reference angle. He used this as being 35, because 35 is something that's easier to use. You just got to make sure that your A value is negative and your B value, because reference angles aren't always the same negative. You'll come up with these exact same numbers, but you might come up with a negative in the wrong place. So just
But it's okay if you do it that way.
Yeah, absolutely, absolutely. But that's when you do that check at the end. Does it make sense that my A? If I would have came up with a positive 237 using your method, I've been like, no, that should have been negative.
Okay.
All right, just make sure your negatives and positives come out. All right, any other questions? That's a good question on bell work. All right, questions on the homework. I'm going to really quickly talk about the homework, really quick. And that is because I had a really good question in the first period. They were just looking at the answer key, and sometimes they would do like 360 minus the number. They might do 180 minus the number. They might do 180 plus a number. They're wondering how to know when to add or when to subtract. And my answer was, it depends on which triangle you solve for. So I'm just going to look at 29. I'm not actually going to solve it unless you need me to. I just want to kind of look at what's happening and why the book did it different ways each time. So if I'm looking at 3, -1, what they're saying is 5xy thing, we'll make this 1, 2, 3, -1. They're talking about a vector, that's right. That is a terrible SnapGrid decision. There we go. They're asking for, what is this angle for this given vector? Now, we know we're using the point 3, 1, so this distance is 3, and this is -1. So if we have two triangles we can solve for, we can either solve for this triangle, so maybe I'll mark that over here. I could solve for that triangle that I have there, which would look something like this, where the top distance is 3, the bottom distance is -1, and I would solve for that angle. As soon as I find that angle, I would have to do 360 minus that angle, and that would give me this full thing here. The other triangle I could solve for is this guy that will look something like this. So now I'd be solving for this angle. This would still be 3, this would be -1. When I solve this angle, I would have to do 270 plus whatever I find. Okay? So if you're confused that when you add 360, when you add 180, when you subtract 180, just do your picture and make sure you know what angle you're solving for. If I'm solving for this one, that's the area that's unused. If I'm solving for this one, it's that whole thing here plus that angle I solve for. Okay? Does that make sense? And I think next year I'll probably add into the homework a little more space and say sketch it as well. It's fine right now, it's just when you study it. We'll have an example today where we have to sketch and kind of decide what we're going to do. All right. Saying that, was there any other questions from the homework? Yeah. 25. So 25 would have been 5. 5, 0. So that means I'm going to move out here. Why are you not putting a point? All right. There. 1, 2, 3, 4, 5. That's the point 5, 0, right? So we're talking about a vector that just lays across the x-axis. What's the degree right here? There's a whole bunch of choices, but what's the smallest? Yeah? 0. That would just be 0 degrees. All right? And what would the magnitude be? How long is this line? 5. So that one actually requires no work, but sometimes those are the toughest ones. Yeah?
So would 360 degrees be wrong? Or?
No. If I would have put in there the smallest directional angle, then it would be wrong.
Okay.
But if I just say the directional angle 360, I'd have to accept it. I'd be like, okay. All right.
Well, you should usually give the smallest.
Usually you give the smallest, yeah. Because, I mean, otherwise there's an infinite number of answers, and I'm not looking for an infinite number of answers. Because I don't want to do 0, 360, 720. I'm just going to shoot for the lowest. Aaron, does that make sense? Okay. Sometimes those are the toughest, the ones where, but I don't have a triangle. Yeah. All right, other quick questions. I'm going to get right into the meat and potatoes. Okay. So let's get into today's lesson. So we're going to continue on vectors. And we're going to start with the scalar product. The scalar product, if you remember from Friday, we said scalar was basically I just multiply the length of my vector. So if I had vector A, 2A would be twice its length. If I had half of A, it'd be half that length. Which is all good and fine if you have drawing and I just have to rough sketch of it. But if I'm given the actual values, all right, my component form, so vector A equals A1, A2, so I could plot those 2 points. What exactly would half that distance be if I was doing a scalar of a half? Well, the way we're going to do scalar product is if we have some number, let's call it K, and that's my scaling effect on A. Remember, if K was 2, it would be twice as long. Well, all we have to do is we just have to multiply that A sub 1 by K, and we're going to multiply that A sub 2 by K as well, and we now have a scalar. All right? So if I multiply basically my A by 2, my B by 2, I'm going to have a line that's twice as long. All right, so scalar is pretty easy. Just multiply your 2 things, your A and your B, by whatever number that is. Vector sum or difference. Once again, we did this. We did this drawing-wise, where we did that tip to tail, where I took A and I added B onto it, and that was my new vector. Well, sometimes I don't want to have to draw it every single time. And this will get us a more accurate representation. So if I'm doing A, if I have A and I'm adding B onto it, graph-wise, I would do tip to tail. But if I'm giving the component forms, I'm just going to say, well, that's A sub 1 plus B sub 1, comma, A sub 2 plus B sub 2. And this is almost going to be the exact same thing as if I use subtraction. So if I do A minus my vector B, that's going to equal A sub 1 minus B sub 1 and A sub 2 minus B sub 2. When I add, it's not super critical I put these in the right order, but when I subtract, it is definitely important. If this was 4 and this was 2, 4 minus 2 is different than 2 minus 4. Yeah?
I forgot what they're called, but do we always use those, like, what are those?
Angle brackets?
Yeah. Do we always use those?
Or triangle brackets, I used to call them angle. Yes. It's going to signify that I have a vector and not a point. Because as soon as I put parentheses on it, you're thinking, oh, it's just a point. These tell me I have a vector, so there's a point starting at 0, 0 and goes out to there. So yeah, we'll always use those angle brackets when we're talking about vectors. All right, the last thing is called the angle product. The angle product is completely different than the other two, and that's because we're going to do A times B. This is the dot product. Now, in my head, I'd be thinking, oh, okay, it'll be the same thing as here. I'll do A sub 1 times B sub 1, comma, A sub 2 times B sub 2. The difference here is when I use the dot product, I'm going to come up with one number. It's just going to be one number. And how that's going to work is I'm going to have A sub 1 times B sub 1. And instead of the comma, we're going to put a plus sign. And now we're going to do A sub 2 times B sub 2. And the whole point of the dot product, without getting into too much super big detail, because this could be a long discussion, this is used to compare vectors. We use that number that we result, and we use it to compare those two vectors. It can tell us whether they're going opposite directions, whether one's big and one's small. So that one number actually turns out to be pretty important. Not so much for what we're doing with vectors, but if you get into more details with vectors, maybe in calculus, you're going to deal more with the dot product. All right, so dot product, one answer. Everything else gives us a coordinate point of the end of a new vector. So when I do the scalar product, I end with a vector. When I add or subtract, I end with a vector. When I use the dot product, I come up with just a number that's used to compare them. All right, let's go ahead and practice these real quick. Well, we have vector W and we have vector Z. The first thing I'm going to do is I'm going to take W and subtract C away from it, or Z away from it. So another way we can note this is just saying that, well, this is negative 3, 2, minus our vector Z, which is 5, negative 1. Well, a vector minus a vector is going to end with a vector. So we're going to have negative 3 minus 5, and 2 minus a negative 1. So that's actually going to be turned into a positive. So be careful. All right, so that's just going to give me negative 8, 3. That'll be an easy enough problem on the test, hopefully. Negative 8 times vector Z can be rewritten as negative 8 times the actual vector, which was 5, negative 1. Well, when I do scalar, I'm just scaling both my A value and my B value. So that's going to equal negative 8 times 5 and negative 8 times a negative 1, which is going to equal a negative 40 and 8. Okay, sometimes we have to do things in a couple different parts. This one is 3W plus 4Z. So the first thing I need to do is I need to figure out what 3W is and what 4Z is. So we're going to do 3W is going to equal 3 times the vector W, which is negative 3, 2. Well, that's going to equal 3 times a negative 3, which is negative 9. 3 times 2, which is 6. I'm going to do 4Z, which equals 4 times, let's just do it a different way. Instead of putting it on the outside, let's put it on the inside. So we're going to do 4 times whatever Z is, so that's 4 times 5, comma 4 times negative 1. Done. Which equals 4 times 5 is 20, negative 4. Now we have to do 3W plus 4Z. So 3W plus 4Z is going to equal, I already know what 3W equals. That equals negative 9, comma 6. And we're adding on 20, negative 4. Well, that's going to equal negative 9 plus 20, 6 plus a negative 4, and that's going to give me 11, comma 6 minus 4 is going to be 2. 11, 2. So if I scale W by 3, I scale Z by 4, and I add those two things together, I'm going to end up with 11, comma 2, which is way easier than drawing all those, scaling them, estimating, and then adding them. And we can do all this just by knowing that endpoint. That's what component form is. It's just that point at the end. All right, the last one is dot product. This is the weird one. This is the one that's not going to end up in a vector. So this is going to equal our W, which is negative 3, 2, times, or the dot product, with 5, negative 1. Well, that's just going to equal negative 3 times 5 plus 2 times negative 1, which is negative 15 minus 2, which just equals negative 17. So our dot product is negative 17. Dot product always comes out with one number. Alright, questions on any one of those four? So those should be quick problems on the test. Quick work. It's just knowing what to do when you see a particular item. Alright. The next thing we're going to do is we're going to find the magnitude and directional angle of the resultant. The resultant. We haven't talked about resultant yet. All resultant says is that we're going to add our vectors. So resultant just means add. We're going to add our two vectors together. All right, that means I need to know in component form, because I don't want to have to just roughly sketch what this looks like. I need to know what the component form of both those vectors are, which is super easy if they give me the graph like this. Because our vector form is just this point with angled brackets on it. Well, this point is 3, 6. So that means the component form of this vector is 3, 6. Our component is just asking for what is this terminal point, and that is 3, 6. For that other guy, we're just going to have the vector form is negative 6, or the component form is negative 6, 2. So those are my two vectors I was given. We just have to add them together, and that will get us our resultant. So to get our resultant, we're going to just do, let's do negative 6, 2, plus 3, 6. Which if we keep going is just going to be negative 6 plus 3, 2 plus 6. And that's going to equal negative 3, 8. Let's go ahead and graph it to make sure it makes sense. Well, the point negative 3, 8, negative 3, 8 is going to be right there. So we end up about there. That is our negative 3, 8. I'm just going to double check. If I do tip to tail, well, that looks about right. That looks about right. So I'm just going to go ahead and draw that vector in, because we're going to need that vector to find the magnitude and the direction. All right, so all this work was just to find the vector we're trying to solve. Now we're going to go ahead and find the magnitude. Magnitude is the easier of the two things to get, because when I'm looking for magnitude, I'm going to call the length of this line r, because a lot of times with magnitude we just use r. Remember that magnitude needs to come out as positive. It will, because we're doing the square root, but just so we are aware that magnitude should be a positive answer. So we're going to find our magnitude first. To find my magnitude, we're just going to have r equals the square root of my a value squared plus my b value squared. Well, in this example, we're going to do r equals the square root of our a squared is negative 3 squared, plus our b, which is 8 squared, which means my r is going to equal 9 plus 64, which is going to be 73. So that is my magnitude. We should always get magnitude right, because it doesn't take a whole lot of thinking. It's just a squared plus b squared, take the square root of it. All right, this is whether either I studied this and I know this formula, or I didn't and I don't know it. The second part is a little trickier. It's not super bad, it just takes a little bit of practice. What I'm looking for the second part, that is my direction angle. My direction angles, I'm looking for that guy. What is the distance from here to here? What angle does that form? So that is my direction angle. So that's my next one. I'm just going to call it direction. Well, to find a direction, I don't have any method of getting this full thing, so I'm going to note that I have a triangle here that I can turn into a right triangle with this point. So I'm going to duplicate that triangle down here. So we're going to duplicate that drawing of that triangle. That's my red. And the point is negative 3, 8. So this point right here is negative 3, 8. You can use angle brackets here. I just use this because I'm just talking about the point. I'm not talking about the full vector. It's just a point that's on this triangle. And the whole point I'm using this for is, well, it's negative 3 in this direction. So this length right here is negative 3. And the height of it is 8. And I'm going to be looking for this angle down here, because I know this angle from here to here is 90 degrees. From here to here is 90. I just need to figure out what is this little extra sliver. So it's 90 plus whatever that is. So if this is my theta here, I'm just looking for 90 plus theta. It's going to be that full arc. Okay, well I have a right triangle. Maybe I should note that. It's a right triangle. That means I can use a trig identity. The only one that doesn't use hypotenuse is tangent. So we're just going to say tangent of theta is going to equal opposite, because tangent TOA, opposite over adjacent. Well, in order to get theta, I need to take the tan inverse of both sides. So we're going to do tan inverse of negative 3 over 8. And I'm going to come up with theta is equal to, other page, negative 20.6. Well, that's a small problem. Because if you just aimlessly answer this question, you'd do 90 plus a negative 20.6, which you'd come up with 69.4. Should this entire angle be 69.4 degrees? Yeah. No, it shouldn't.
Add the 20.6.
Add the 20.6. This cannot be negative. You're just going to turn it into a positive. All right, because that doesn't make sense to subtract it away. So like Chris said, we just have to add it. We have to be aware that this is bigger than 90, so I need to add. So what they're doing right here to negative 20.6 is this angle, like going from here to here. I want to get from here to here. So you got to be smarter than your calculation. So this needs to be positive. So we'll just take the absolute value of it and just say this is 20.6, or like Chris said, just realize you have to add it. You don't have to do anything, just be like, meh, can't subtract it, need to add it. So that's going to give me 90 degrees plus that 20.6 degrees is going to equal 110.6 degrees. That is my directional angle. So this whole thing is 110.6 degrees. Yeah?
For the direction, is it always going to give you a right angle? Or no?
For the direction?
Yeah.
It has to. Whatever point, do you see how there's actually two right? I could have did a right triangle here too.
Oh, okay, yeah.
I could have did a right triangle here and did 180 minus whatever I got here. Yeah, because it's just a point that has to form a right triangle. That's what trig is based upon, that my xy plane, I can always make a right triangle out of it. Okay? Does that make sense, I guess? Okay, good. All right, other questions on this one, because there's a lot of material on here. This is basically everything we did. This is the hard stuff we did yesterday, along with a little bit of new stuff. Yeah?
Just one more question then.
Yeah.
Would you need the... Oh, never mind. I figured it out.
Okay. You want to ask it anyway?
No, because I realized... Well, like...
But someone else might have it, and they're just...
I was going to ask, like, why you needed the magnitude line for the direction, but now I realize why.
Oh, okay.
I just didn't think before I asked.
Gotcha. Okay. Good on that? A lot of stuff happening on that one. So that's a really good problem. All right, angle between vectors. What I'm talking about is, hey, I have vector A. I'll label them in a second. I have vector B. This is actually a pretty cool thing. I have vector A and vector B. We can actually find that angle that's between them. I'll just call it alpha. I can actually find that as long as I know some information about A and B. And this is going to be our dot product theorem. So we're going to use something called the dot product theorem. And what the dot product theorem says is if I take the cosine of alpha, that's going to equal the dot product of A times B over the magnitude of A times the magnitude of B. So I'm going to put that down. This is my dot product. And these are magnitudes. So that means I need two things. I need to know the component form of A and B, and I need to know their magnitudes. All right, those are the two things I need, and I can use the dot product theorem to get that angle that's in between. All right, so like I said, the dot product was used to compare things. When we use the dot product to come up with angles between vectors, we can actually come up with three concrete things. We can actually come up with more, but we're just going to stick with three right now. First of all, if A and B have the same direction, the angle between them is 0 degrees. So your cosine is going to equal 1. So if your dot product comes out as 1, you know both your angles are going in the exact same direction. In fact, they're parallel to each other. They're running parallel to each other, or they could be the exact same angle. Also, if A and B have opposite directions, that means they're parallel, but they're going in opposite directions, kind of like that guy. The angle between them is 180 degrees, so that means your cosine is going to equal a -1. So if you get out 1, or if you get out -1 from this, you're going to know that your lines are parallel. These indicate that you're parallel. If A and B are perpendicular, you're going to come up with your cosine equaling 0. So that means they have a 90-degree angle if your cosine equals 0. So if you come up with 1 or -1, they're parallel. If you come out with 0, it means that they're perpendicular. All right, so those are three big things to know. If it's -1, they're running in opposite directions. If it's a +1, they're both going the exact same direction. We don't know where they are. They might be way over here and one's over here. All we know is they're going the same direction and they're parallel to each other. All right, let's go ahead and use that to find this. So we're supposed to find the smallest positive angle between each pair of vectors. Like I said, we need two things. We need component form and we need magnitudes. Well, they gave us the component form, so we just need to find the magnitudes to start off with. So I'm going to call that my mags. I'm going to find my mags. When you're dealing with vectors, whenever you put an absolute value sign down, it automatically assumes that we're talking about magnitudes. And to find magnitudes based upon vector form is pretty easy. All you need to do is take the square root of a squared plus b squared. So that's going to be -3 squared plus 2 squared. Well, that's going to equal 9 plus 4, so that's going to be the square root of 13. Now I just need the magnitude of the other one, which would be 4, 5. Do the exact same setup, square root of a squared, which is 4 squared, plus b squared, which is 5 squared. That's going to equal 16 plus 25, so that's going to be the square root of 41. So that's my magnitude. Maybe I'll put a little line saying I'm done with magnitude, I'm on to something new. Now we're going to put this in the dot product. We need the dot product to find that angle. So dot product says that the cosine of that angle in between is going to equal the dot product of the two vectors, so that's going to be -3 2 times 4, 5, all over my magnitudes, square root of 13 times each other. All right, remember our dot product should end up with one number. We're going to do our A times our A, which is going to give me, let's go ahead and just continue on. Our A times our A sub 1 times our B sub 1, so negative 3 times 4 is going to give me negative 12, plus 2 times 5, which gives me 10. I don't have a ton of room here. Maybe if you have room, put a little note to yourself, because you're going to be studying this later on, that this is actually negative 3 times 4. And this is 2 times 5. Because I don't know if you're anything like me, but when I study for a test 2 weeks from now, I'll be like, how did I come up with 12 and 10? Especially when you're studying for finals, and you come up to this question, you're like, where did I get those numbers from? All right. So that'll be over. I'm just going to leave this as square root of 13 times square root of 41. I'm just going to let my calculator deal with that on its own. All right. I have cosine alpha equals some number right now. So I'm going to want alpha equals cosine inverse of negative 12 plus, so that's negative 2, over square root of 13 times square root of 41. Which you will need a calculator most likely. And you should come out to 94.97 degrees-ish. Or 95 degrees. Question, or are you about to stretch and then you decided not to when you saw it draw attention to yourself? Okay, any questions on that one? So angle between. You need your component form, you need your magnitudes, and then you throw it in the dot product theorem, which your top should come up with just one number. If you come up with a vector, you're going to be like, I don't know what to do now. So you need to come up with one number, and then divide it by our magnitude times our magnitude. All right, for our next one, I'm not going to go through it all. We have 5 minutes, but I'll give you time to work on it on your own if you have homework you want to do. I'm going to tell you right now, this should come out to cosine of alpha equals 0. That was the big part about that cosine alpha equals 0. Because I want you to realize if it comes out to 0, 1, or negative 1, you know something important about it. And what do we know if our cosine alpha equals 0, based upon those 3 statements we read right before? Look at those 3 statements again if you're not sure. Yeah? They're perpendicular. Because if you go back here, it says right here, if cosine alpha equals 0, they're perpendicular, it's 90 degrees. So this is going to tell me they're perpendicular. Which means it's 90 degrees. If you didn't realize that, that's okay, because what you probably would have did is you did alpha equals cosine inverse of 0, which you'd come up with 90 degrees either way. But I believe there's homework I put on there. I can't remember if I put it on or took it off. But you have to say whether it's parallel, perpendicular, or neither. So you're looking for 1, negative 1, or if it equals 0. That way you're done. You don't do anything else after that. Okay? So work on this problem. See if you can get it done.